right, wave interference part 4. We talked about how you can set up standing waves on a string by adjusting, there's 3 things that are related: the velocity, the wavelength, and the frequency. And you can, for example, fix the frequency and adjust the velocity till your wave fits the string, or you can fix the velocity and vary the frequency until your wave fits the string. You can also set standing wave up in air columns. This is how musical instruments work. The main distinction there is whether or not we're going to have a fixed end or an open end. So here's a pipe, could be an organ pipe, and we're going to blow, like we could take a tuning fork that plays a particular frequency and set up a standing wave. And so different waves will fit because of the speed of the sound in the air and then the frequency at which we're trying to drive the pipe. So if we vary the frequency, we'll hear a resonance at a particular case. In other words, we'll hear this suddenly get louder. And you've all done this: put water in a Coke bottle. I guess we don't have glass Coke bottles anymore. It'll work on a plastic one too, and you blow over it. And if you put different amounts of water, change the column, then you get it to resonate at different frequencies. Sounds high, sounds low. Well, that's what's going on here. So for a pipe open at both ends, then you can have an antinode at either end. And so the longest wave that would fit, the biggest wave that would fit, would have one node. So that, each one of these is a quarter of a wave. So that means the length of the pipe would be 1 2/4 or a half wave. Or the frequency, which is velocity over wavelength. If you know the velocity in the air, would be 1 over 2L. Then if you increase the frequency, you pick a different tuning fork to do over the surface of that top of that pipe. The next wave you could set up would have, again, you got to have antinodes at the end, but you could have an antinode in the middle. In other words, one node, now you got 2 nodes. And if you count 1 2 3 4 quarters, so the wavelength of the pipe, the wavelength of the wave would be the same as the pipe. Notice V over L, compare that to the other one, that's going to be twice what the fundamental was. It's also fundamental, first overtone, second overtone, also called first harmonic, second harmonic, third harmonic. What's the next one? Well, you can add another node. So you've got 1 2 3 4 5 6 quarters. 6 quarters is 3/2, so the length of the pipe is 3/2 times the wavelength of the wavelength's 2/3 of the pipe. So open at both ends. And you can keep going and have other harmonics. And that could be, like I said, an organ pipe, could be a flute, could be a clarinet, which has fixed lengths. And then you're going to start the noise by vibrating a reed or vibrating your lips and blowing air. So the other case could be when you have a closed end of the pipe, and that's going to change what will fit because you've got to have a node and an antinode. Antinode's always at the open end of the pipe. So you could the largest wave in there would be, well, you only fit a quarter of it in there, so the length would be a quarter wavelength, or 4L for the wavelength. Put another node in, you got 1 2 3 quarters. So L is 3/4 wavelengths, or flip it over 4/3. And again, fundamental, first overtone, second overtone, first harmonic, third harmonic, fourth harmonic. And they're related to the fundamentals. And so I can take the same pipe, and whether I close it or open it, I'm going to hear it resonate or play sound at different frequencies, depending on whether one end's open and one end's closed. Notes about instruments, and you people who played instruments in the band know this better than I do. Sounds produced by air columns become sharp depending on as the temperature rises. Sounds produced by strings become flat. Those are environmental conditions that influence the things that we're talking about. Musical instruments based on air columns are generally excited by resonance. In other words, you put multiple frequencies in one end, and it's only going to be able to resonate or set up a standing wave for the frequencies that fit that condition. Same thing's true for the string. A demo we used to do, and I don't have the equipment anymore. Now that we're recording, I should have recorded this one. Maybe I'll look out there online and see if I can find it. But what you do is you take a pipe, usually plastic or glass, and put water in it, and then you adjust the amount of water in it, and then you adjust the water until you can make it resonate or match the frequency of a tuning fork. And it's really significant. You can hear the difference significantly. When it's not at the right length and you don't just hear the regular fork, but when you raise or lower it, you can hear that significant. And again, that would be closed and open, so the fundamental or first resonance would be quarter wave, 3/4, 5/4. More complicated situations like a drum head, standing waves on membranes. When you play a drum, you can set up different wave patterns on it. This is a nice, again, you can probably search it, find a video of this one of people putting beads or something on the drum and then beating the drum and watching it set up for different patterns. So the idea is more complicated but similar for percussion instruments also. Another type of interference from standing waves is beats. Beats is a little bit different. It's when you have waves coming to a point, but they're not exactly the same frequency or wavelength. Then you hear a phenomena that we call beats. So let's go over here and look on web and pull my beat simulation. There we go. All right, so you've got two waves. If they're exactly the same frequency and they arrive, then this is the combined. I got two waves. It should be a red and a blue, but a green and a blue. They're on top of each other. Makes us a red. So it's just twice as big. But if we have one of them, say, let's go down to 25. They start out in sync. This is the sum of the two down here. Since they're doing, a little bit different frequency, they're not quite in phase, and sometimes they'll match, sometimes they won't. That's called beats. And so what you'll hear here is you'll hear the sound go loud, short, small, loud. The sound you'll hear will be an average of the two. So 30 and 25 would be somewhere around 27, and we would hear it modulated. People who play stringed instruments, that's the way you learn to tune a guitar, is you play two adjacent strings, and you listen for the beats. When it's out of tune, then you'll be able to hear that. If it's close, you'll be able to hear that modulation, and you tune to get rid of it. You can make that a little more pronounced. Let's set this up to about 40 and 42. It's also how we send radio waves. It's called a modulation. You got AM and FM, different ways to modulate waves. You have what's called a carrier frequency. And you're taking your frequencies of your voice or your musical instrument and you're adding them to a given frequency, and then you look at the modulation, depending on its amplitude or frequency modulated, to pull out the signal by subtracting the modulated wave. So there's another one. So you hear, here's as the amplitude goes down, it gets quieter and quieter. Sometimes it'll fade away and then it'll start to grow big, but you hear a particular frequency, which would be the average. So those are pretty close. The beat frequency, I think, is half the difference. So that's beats. Yeah, when you add those two up, then you get half the difference of your resulting amplitude. And there's the simulation I just ran. There's some different ones you can try with it. Now, a musician, certainly not me, but a musician who listens to music a lot, can listen to two different instruments that are playing the same sound, can hear those recorded and tell you what instrument it is, because there are a lot of different qualities, timbre, pitch, and other things that go into make why an instrument sounds the particular way it does. And one way we have of taking a complicated sound and breaking it into the various frequencies it composes called Fourier analysis. So in other words, I can play a tuning fork, and here we plot out the frequencies, and it's a single frequency. And it's just a nice sine wave. But I could play the same note on a flute, and it would sound different than on a clarinet because they have different combinations of their standing waves. And so what we have here, and my picture's in the way, is they've taken a flute playing a C, I think, and they looked at there was really more than a single frequency. And that's why it makes it sound a little bit different than if I did, for example, a clarinet. Even though that, you know, we would say it was the same note, there's a different combination of all the frequencies that go into it. These tell you the amplitude, so even though some of those frequencies would be the same, they're a different mix. Some of them are louder in the flute than the ones in the clarinet. And that's called Fourier analysis, where we can take it and break it up into its component frequencies. And that's how digital works, is you know what combinations give a particular quality to the music. So you can just take the raw notes and combine them to make it sound like a flute or a piano or whatever it might be. Similar to those in differential equations are going to be doing Laplace transforms at the end for solving differential equations. Those are for some types of problems. The problems that involve repeating patterns, very similar, but it's called Fourier analysis, Fourier series and Fourier transforms. So I can take basically the right frequencies and reproduce almost any sound. The standard one that you do is called a square wave. To illustrate that, here's another app that's in our problems. And so a square wave is just like it is here, is, you know, plus some number, then it drops to minus and plus, so it's not rounded. But what I can do is I can begin to build it up by the right combinations of frequencies. So there's the basic one that would match the pattern, and then I can add, there's three together. Let's go up to say 5, and these are all the odd ones. Come up a few more, and you can see as we add more and more waves, it gets more and more square. We can even with 25 different frequencies, we can do a pretty good job of reproducing that square wave. Again, that's sort of the basis behind how digital electronics works. We can take individual frequencies, adjust the intensity of that frequency, and reproduce any particular sound that we want. And there's how to run that. And that gets us into, you know, we've studied particles, and we did most of the first part of physics on mechanics of particles, how things move, and we talked about electrons and protons. And we've talked about waves as if they're two different things. What we learned in modern physics is that that's not really the case when we talk about the things that make up the atoms. We talk about them, and sometimes they act like particles, but we can't explain all the things that happen with them. Sometimes they actually act like waves. We'll talk about it for light in particular. Light's the same way. We'll talk about photons. We'll talk about electromagnetic waves, and in different scenarios, they act one way or the other. I think the modern understanding is that the small particle nature, things that are small that make up the atoms, they're not either really particles or waves. They're something else. The things that we know how to describe are particles and waves, and so we can use that to describe different phenomena. We talked about how the Bohr model of the atom, you can think of electrons rotating around the neutron, but there's really no reason why they would only have fixed orbits. Classically, they could have any orbit, but if you realize the electron is a particle, a wave, and that its wavelength depends on its velocity, and the velocity depends on the distance from the orbit. You can only have the electron be there when you have a constructive interference. Just like you only get the standing waves on the string when you match the right velocity. So, and that works out quite well if you calculate the size of the wave for the electron, then that matches exactly the Bohr orbits. So particle-wave duality. So that's why we spend so much time talking about particles and waves, because we think they're fundamental to how things work. So are two different modes of describing things. Alrighty, well that's our last lecture on standing waves. I'll post problems and some videos about how to work the problems